Okay, so let's talk about something that gets to the absolute heart of how science works. When you've got two different scientific theories and they're both trying to explain the same thing, how do we actually decide which one is better? Who's the winner? It's a huge question, and the answer, well, it's probably not what you think. So just think for a second. What makes a scientific theory feel strong to you? What's that secret sauce that makes one idea rise to the top while another one falls away? I bet for most of us, the first word that pops into our heads is evidence, right? It just feels like common sense. The more evidence you have, the stronger your theory is. I mean, a theory with 1,000 pieces of supporting data has to be better than one with only 10. It's just a numbers game. Or is it? Imagine your theory is super simple. All crows are black. So you go outside, you see a black crow, check. You see another one, check. And another, and you do this 999 times. You've got a mountain of evidence, right? You're feeling pretty good about your theory. But is that really the best way to do science? Well, it turns out there's a much more powerful, much more rigorous way to look at this. It's not about just collecting wins. It's about putting a theory through a real trial by fire. And this is where we need to introduce a new concept, corroboration. So what is corroboration? It's not about counting how many times a theory was right. It's an evaluation of how severe the tests were that the theory managed to survive. It's a total shift from quantity to quality. It's about a theory proving its mettle, showing how tough it is when things get really difficult. And here's that shift in a nutshell. The old way of thinking, the common sense way, is just to count the supporting examples. But the corroboration view says, nope, forget that. What really matters is the severity and the diversity of the hurdles that theory has cleared. This quote really gets to the soul of it. Scientists aren't looking for safe theories that are probably true, but also kind of boring and don't tell us much new. Like, it might rain tomorrow. What they really want are theories packed with information, bold, specific, risky claims about how the universe works that can then be put to the test. Okay, so if the goal is a bold theory, what does that even look like? How do you build a theory that's even worthy of going through this trial by fire? Well, it all boils down to one crucial feature: testability. And a highly testable theory really has three main ingredients. First, it has higher universality. It applies to more stuff. Second, it has greater precision. It's super specific. And third, it has simplicity, which means it has fewer moving parts to fiddle with. Let's dig into each of these. First up, universality. Let's say your theory is all planets move in circles. That's a pretty bold claim. But what if you made it even bigger? All heavenly bodies move in circles. Whoa, now you're talking about planets, comets, moons, asteroids, the whole shebang. Because it covers so much more ground, there are way more opportunities to prove it wrong, and that makes it a riskier and therefore a much better theory to test. Now, this next one, precision, can feel a little backwards at first. So, a theory that says all orbits are ellipses is actually less precise than one that says all orbits are circles. Why? Because a circle is just one very specific type of ellipse. The circle theory is way more restrictive. It gives you no wiggle room at all. That makes it incredibly easy to prove wrong. And in science, that's a good thing. A super specific theory that survives testing is way more impressive than a vague one that could mean anything. And finally, simplicity. Now, this doesn't mean the theory is easy to understand. It means it has fewer moving parts, or what scientists call freely determinable parameters. Think of it this way. A complicated theory has a bunch of dials and knobs you can tweak to make the theory fit the data. A simple theory has almost none. It makes a direct take-it-or-leave-it prediction that's much, much easier to test. All right, so now we know how to build a bold, testable theory. Now, for the main event, the tests themselves. And this is really where that idea of quality over quantity comes into play. Let's go back to where we started. So here we have theory A, with just a ton of supporting evidence. And then there's theory B, with only a handful of positive results. Just looking at the chart, at the raw numbers, theory A looks like it's crushing it. So it's obvious, right? Theory A is the winner. Case closed, isn't it? Well, not so fast. Because as it turns out, just counting up the wins is not the measure of a good theory. What you have to look at is the severity of the test that theory actually survived. So what makes a test severe? It's all about doing something new and different. Going out and seeing your 1,000th black crow is a low-severity test. You're just doing the same thing over and over.
but a single, brand new experiment that tests the theory in a totally unexpected domain, like Millikan's incredible experiments measuring the charge of an electron. That is a high-severity test. One test like that can be worth more than a million repetitive ones.
So let's pull all these threads together. How does science finally reach a verdict? The best way to think about it is as a constant, fierce struggle for survival between competing ideas. This table really spells it out. The number one priority, the most important thing, is the theory's built-in testability and simplicity. Is it a bold, risky claim? Next, and still super important, is the diversity of the evidence. Has it survived tough tests in new and different areas? And way down at the bottom, with low priority, the total number of positive results. The quantity of evidence is a really poor way to judge a theory compared to the quality of the tests.
So you see, scientific progress isn't this gentle process of collecting stamps in an album to prove a theory. It's this dynamic, aggressive, critical process. We seek out the boldest, riskiest, most testable ideas we can find, and then we try with everything we've got to break them with the most severe tests we can possibly imagine.
And I'll leave you with this amazing thought. Science is basically a kind of Darwinian evolution, but for ideas. We don't just pick the theory that's the most popular or has the most likes. We select the one that proves itself to be the fittest by surviving the absolute fiercest struggle for survival that we can throw at it. So the next time you hear about a new scientific discovery, don't just ask, how much evidence do they have? Ask, how hard did they try to prove it wrong?